All right, I've got a great little brain teaser for you today. On the surface, it seems super simple, but it actually hides a really deep and honestly beautiful mathematical secret. Let's get right into it. This is the puzzle of the two cups.
So here's the challenge. Imagine you have an endless supply of water from a tap. Your only tools are a 3-ounce cup and a 5-ounce cup. That's it. Your mission is to use just these two cups to measure out exactly 4 ounces of water.
Now, here's the catch, and it's a big one. There are absolutely no measurement lines on the cups. You can't just eyeball it and say, hey, that looks about right. You can only do 3 things. Fill a cup all the way to the top, pour water from one cup into the other, or dump a cup out completely.
So how would you do it? Seriously, if you want, just pause for a second and think about it. The cool thing about this puzzle is that there's no single gotcha answer. There are actually a couple of different, totally valid ways to get to 4 ounces.
So let's explore those two paths. Both are super clever and both get us exactly where we need to go.
All right, the first approach is what I like to call the subtraction idea. You're basically thinking, okay, I need 4 ounces. Well, 4 is just 5 minus 1. So the real puzzle becomes, how do I isolate exactly 1 ounce so I can take it away from 5?
Now here's how the original source material lays out the steps. I know, looking at it like this, it can seem a little complicated. So let's just forget the text for a second and walk through it visually, one move at a time. Okay, you ready? Here we go. Step 1, fill the 5-ounce cup all the way to the brim. Simple. Step 2, now carefully pour from that 5-ounce cup into the 3-ounce cup until it's full. And boom, you've just left exactly 2 ounces behind in the big cup. Step 3, dump out the 3-ounce cup. It's empty again. Step 4, pour those 2 ounces you saved into that now empty 3-ounce cup. Step 5, go back and fill the 5-ounce cup all the way up again. And here it is, the final genius move. Step 6, use that full 5-ounce cup to just top off the 3-ounce cup. See, it already has 2 ounces in it, so it only has room for 1 more ounce. And what are you left with in the big cup? 5 minus 1 is exactly 4 ounces. Problem solved. But maybe your brain didn't go down the subtraction route at all. Maybe you thought, hey, wait a minute, 4 is just 3 plus 1. And you know what? That works too. This is the addition idea.
And again, here are the formal steps from the source. It's a completely different sequence of pours and fills, but the logic is just as elegant. So let's break this one down too.
Let's do this. Step 1, fill the 3-ounce cup and dump the whole thing into the 5-ounce cup. So now the big cup has 3 ounces in it. Step 2, fill that 3-ounce cup up again. Step 3, now use it to top off the 5-ounce cup. The big cup only needs 2 more ounces to be full, right? So when you pour, you're left with exactly 1 ounce back in your little cup, and that 1 ounce is everything. Step 4, empty the big 5-ounce cup. Step 5, pour that single precious ounce into it. And for the grand finale, just add 1 full 3-ounce cup, and what do you get? 1 plus 3 is 4 ounces. Perfect.
So we solved it, twice. But honestly, the real lesson here isn't about what you can do. It's about what you can't. So now, let's take on the impossible challenge. Let's just change the rules of the game a tiny bit. What happens if we're given a completely different set of tools?
Here's the new problem. You've got a 4-ounce cup and a 6-ounce cup. Your goal is to get exactly 5 ounces. It feels like it should be possible, right? But it's not. I'm telling you right now, it is absolutely impossible. And the really cool question is, why?
Well, the answer lies in a really simple mathematical rule that was actually hiding in plain sight this whole time.
Okay, so check this out. Just look at your tools. You have a 4-ounce cup and a 6-ounce cup. What do you notice? They're both even numbers. So think about it. Every single thing you can do, filling a cup, pouring from one to another, will always result in an even amount of water. You can get 2 ounces, 4 ounces, 6 ounces, but you are mathematically trapped. You can never ever land on an odd number like 5.
You know that gut feeling, that even number intuition? It actually has a formal name in number theory. It's called the greatest common divisor, or GCD. All that means is it's the biggest number that divides both of your starting numbers perfectly, with nothing left over.
And this is where it all just clicks into place. For our first puzzle, with the 3 and 5-ounce cups, the greatest common divisor is 1. 1 is the only number that divides both. And when the GCD is 1, it's like a magic key. It means you can eventually make any whole number you want. But for our impossible puzzle, with the 4 and 6-ounce cups, the greatest common divisor is 2. And that's the hidden rule. It means you are locked in. You can only ever make amounts that are multiples of 2. And since 5 is not a multiple of 2, the puzzle is impossible.
So you see, this little game with a couple of cups isn't really about water at all. It's about understanding the fundamental rules that govern numbers and how those rules define what is even possible.
And believe it or not, people have been wrestling with these ideas for ages. The core math behind this, the GCD, was figured out by Euclid way back around 300 BCE. Versions of this puzzle have been stumping people in books for centuries, and it eventually became this classic way to teach problem solving. It just proves that even when the numbers are small, the ideas behind them can be massive.
And that really brings us to the biggest takeaway here. A puzzle like this does more than just make you think. It's a perfect example of how mathematics isn't just about finding answers. It's a language that describes the very limits of our world, explaining with absolute certainty not just what we can do, but also what is fundamentally and forever impossible.